In this video, we're going to talk about a few details that you need to pay attention to in order to make your op-amps actually work. This one will save you a ton of frustration in the lab if you pay attention carefully. I've reminded you that op-amps have power rails a few times through this series of videos, but so far we've skipped talking about the power supply connections. The technical details of them aren't very tricky, but they will definitely cause you a ton of grief if you don't pay attention to them. In particular, these power supply voltages set the maximum and minimum output voltages of the op-amp. So when I say the op-amp rails, I mean that it goes to the value of V+, or it goes to the value of V-. One really common mistake is asking your op-amp to produce a voltage outside of these rails. So your op-amp will look like it has a constant output in that case, which is a failure mode that students are usually confused by. Another common mistake is not providing power to op-amps at all, and like any circuit, they work better when the power's on. So remember to plug in your power rails and to check that your desired output voltage falls in between them. Now, when you're plugging in your power supply, you need to read your datasheet carefully, because different op-amps have different power supply requirements. You're likely to run into two broad classes of op-amps, which are called dual supply or dual rail, and single supply or single rail. Dual supply op-amps, like this guy, need to be provided with two voltages, one of which is positive and the other of which is negative. So this plus V and this minus V. Usually those are the same value, so it needs plus or minus 20 volts and not plus 20 volts and minus 10 volts. These op-amps guess where ground is based on the positive and negative voltages provided to them, which is why you usually want the symmetric plus and minus 20 volts. Because these op-amps have a negative voltage as one of their supply rails, they're capable of generating negative output voltages. So you can build a DC, zero offset inverting amplifier out of this type of op-amp. Single supply op-amps are different. They require a positive voltage and ground on their terminals. That means that these op-amps can't generate negative voltages, but they tend to be easier to build because negative voltages are hard to come by in battery-powered systems like your robot. So be sure to check your datasheet to find out if your op-amp is dual supply and needs a negative voltage, or if it's single supply and it needs ground as its bottom rail and possibly an offset voltage on V+. While you're looking at your datasheet, there's another thing to check. Not all op-amps have the ability to drive their output all the way to their rails. Some op-amps, especially older ones, need a little bit of margin between their input and output voltages and the power supply rails to work correctly, whereas newer op-amps tend to have something called rail-to-rail input and output. Most op-amps advertise whether or not they're rail-to-rail right on the front page, so you should be looking at the features section, which is usually in the upper right, to see whether or not your op-amp works this way. I've included two features sections here from op-amps that we use, and the MCP 6004 is rail-to-rail, while the OP-A 551 is not. And just a quick bit of vocabulary, the range of acceptable input and output values is referred to as input or output voltage swing. So finally, it's worth talking about decoupling capacitors, which are also called bypass capacitors, and I'll use the terms interchangeably. And those are capacitors that are pictured here. These are capacitors that go from your power supply rails to ground, and they might not seem like they're doing anything important, but if you skip them, you can get in big trouble. Not having bypass capacitors will eventually cause one of your circuits to have big random-looking output, and students usually call that output noise, but it isn't actually random and it isn't actually noise. It's a stability problem in your op-amp. And that stability will corrupt your measurements like crazy. It will mean your op-amp only gives you garbage. Putting these capacitors on your op-amp helps to keep it stable, which is really important because instability can creep up under weird conditions, like with different temperature or with different mechanical strains on your breadboard. So we encourage them strongly as a precaution to make sure your data always gets saved. Now, the full details of how bypass capacitors work are outside the scope of this class, but you can get a rough idea of what's going on by thinking about the fact that these are connected between your power supply rails and ground. This means that they act like low-pass filters on the power supply. So another way to think of that is if your chip sucks some charge out of the power supply in order to operate, the bypass capacitors are like big buckets of charge which don't change their voltage level very much when your chip starts pulling current. So bypass capacitors keep the supply still. Why does that help with stability? Well, you learned in E79 that normally stable systems can become unstable when they have the wrong kind of feedback. We deliberately add the right kind of feedback between the op-amp output and the op-amp input. That's negative feedback and it's stable. But sometimes there's accidental parasitic feedback paths between the op-amp output and the op-amp supply rail that occur inside of the op-amp. These feedback paths can make the op-amp unstable, but bypass capacitors are usually sufficient to suppress them. One last note, when you're putting in bypass capacitors, you actually need to use different values of them in parallel. So this is 100 nanofarads and 10 microfarads. This might seem weird because 100 nanofarads in parallel with 10 microfarads seems like almost no capacitance at all. But it's important because capacitors have some secret parasitic components inside of them that work differently at different frequencies. If you're not sure what values to use, default to the values shown in the datasheet, or failing that, the values on this slide. Notice that this slide shows both positive and negative supplies of a dual supply amplifier being bypassed to ground, which is usually necessary. You need to bypass both V plus and V minus. It isn't necessary to bypass a ground rail to ground in a single supply amplifier because they're both at the same voltage. So, in summary, your voltage rails define the output range of your op-amp. Dual rail op-amps use both positive and negative voltage rails so they can generate negative voltages. Single rail op-amps use positive rails and ground so they're easy to implement, but they can't make negative voltages. Check your datasheet to see whether or not your output can go all the way to the rails or if it needs some margin, so look for rail-to-rail inputs or outputs. And bypass capacitors are really important to keep your op-amps stable and your data safe, even under varying conditions.